In 2012, deep beneath the border of France and Switzerland, scientists smashed particles together and found something they had chased for half a century: the Higgs boson. Headlines called it the God particle, the thing that gives everything its mass. Case closed, or so it seemed. Look down at your own hand. Almost none of its weight comes from the Higgs. Your true mass is stranger, hidden inside every atom, powered by the strongest force in nature and by energy disguised as matter. If puzzles like this keep you curious, tap like and subscribe. Ahead, a particle that should be trillions of times heavier, ghost particles that break the rules, an empty space heavier than every star combined. So where does mass really come from? Get ready, we begin. Picture a room packed with scientists. Some are grey-haired, some are shaking. All of them stare at one glowing screen. It is July of 2012. Deep under the ground near Geneva, inside a machine 17 miles around, protons have been smashed together billions of times, and in the wreckage a signal appears, a tiny bump on a graph. The room erupts, people hug. One old man wipes tears from behind his glasses. His name is Peter Higgs, and the thing on that screen carries his name. They had found the Higgs boson. For almost 50 years, this particle had been the most wanted object in all of physics. Scientists built the largest machine humans have ever made just to catch it. They cooled it colder than deep space. They spent close to $10 billion, and now they had their prize. The news raced around the planet in hours. Newspapers reached for a nickname, and one stuck like glue. They called it the God particle, the thing that gives everything its mass, the reason you have weight, the reason stars hold together, the reason anything exists at all. Editors wrote that the mystery of mass was finally solved. Case closed. The universe made sense, except those headlines had it wrong. The Higgs is real. The discovery ranks among the greatest moments in the history of science, and nobody serious doubts it. But that famous nickname hides a secret the celebration skipped over. The Higgs explains only a thin slice of where your weight comes from. Look down at your own hand. Almost none of what makes it heavy has anything to do with the Higgs at all. To see why, you have to understand a question so simple that most people never stop to ask it. What is mass, actually? Where does the weight of you, of me, of this whole planet truly begin? The answer will take us somewhere far stranger than a bump on a graph. It will take us inside the atom, into a roaring storm that never stops, powered by the fiercest force in all of nature. And the first surprise is waiting in something you do every single day without thinking. Push a shopping cart across a flat parking lot. An empty one rolls easy. Now load it with bricks and push again. Your arms strain. The cart fights you. That fight, that stubborn refusal to get moving, has a name in physics. It is called inertia, and it is the truest face of mass. Most people think mass means weight. Weight is the pull of gravity, how hard the ground yanks you down. Mass is deeper. Mass is how hard it is to change the way something moves. A bowling ball floating in empty space weighs nothing at all, yet shove it and it barely budges. It still has mass. It still fights back. Here is a picture that makes it click. Imagine kicking a soccer ball, then kicking a cannonball painted to look exactly the same. Your foot expects a soccer ball. Your foot gets a broken toe. The cannonball resists because it holds far more mass, even though the two look identical sitting still. So mass is resistance. It is the amount of stuff something is built from, measured by how stubbornly it clings to whatever it is already doing. For thousands of years, nobody asked where that stubbornness comes from. It seemed too obvious to question. Things have weight because they are made of stuff, and stuff is heavy. End of story. Then physicists went hunting for the smallest pieces of that stuff. They broke matter down into atoms, then broke atoms into even tinier specks, and down at the bottom they found something that made no sense. The tiniest building blocks, the particles at the very floor of reality, should have had no mass whatsoever. Zero. According to the best math scientist had, these particles should weigh nothing and blast through space at the speed of light forever, never slowing, never clumping, never forming a single atom. If that math were the whole truth, you would not exist. No planets, no stars, no chairs, no bones, no oceans, just a cold flash of weightless particles racing apart in the dark. Clearly something was missing. Something reached into that perfect empty math and handed the smallest particles their weight. Something forced them to slow down and stick together into everything you see. Finding that something became one of the deepest quests in all of science. And the trouble that started it was buried inside the most beautiful theory physicists had ever written. By the 1960s, physicists thought they were close to a dream. They were building one grand theory to explain every particle and every force, a kind of master rulebook for reality. When it worked, it was gorgeous. The math was clean, the predictions were sharp, experiments kept proving it right. The theory had one humiliating flaw. It insisted that every fundamental particle must be massless. Think about what that means. The tiny particles that make up light, called photons, really are massless, and they really do fly at light speed. Good. The math loved that. But the same math demanded that the particles making up your body must be massless too. It demanded that electrons weigh nothing. It demanded that the tiny pieces inside protons weigh nothing. Everyone knew that was false. Electrons have mass. Scientists had measured it. You can hold a rock and the rock is heavy, so the pieces inside it cannot all weigh zero. So physics had a crack running straight through its most prized theory. Add mass to the equations by hand, just force the numbers in, and the whole structure collapsed. The beautiful symmetry shattered. Predictions turned into nonsense, spitting out impossible answers like infinite probabilities. Picture building a bridge with flawless blueprints, then realizing the blueprints only stay flawless if the bridge is made of nothing. The moment you add real steel, real weight, the design falls into the river. That was the mass problem, and it was tearing at some of the smartest minds alive. The theory was too accurate to throw away and too broken to accept. For years it just sat there, a splinter no one could pull out. The fix, when it came, would sound almost insane. Instead of forcing mass into the particles, what if mass was never really theirs to begin with? What if the particles stayed massless at heart, and something outside them, something spread through all of space, gave them the weight they seem to carry? Imagine an invisible ocean filling the entire universe, an ocean with no colour, no smell, no way to see or touch it, sitting silently in every empty room, every gap between stars, every space inside your own chest right now. Particles would swim through this ocean, and the ocean would drag on them, and that drag would feel exactly like mass. It was a wild idea, a hidden field flooding all of reality, handing out weight from the shadows. Most people would have laughed. A quiet young physicist in Scotland did not laugh. He picked up a pen, and what he wrote down would take almost half a century to prove, starting with a single equation scribbled during a walk in the hills. In 1964, a shy physicist named Peter Higgs went walking in the Highlands of Scotland. He was chewing on the mass problem, the splinter no one could remove. Somewhere among the hills, an idea struck him so hard he later said he had seen the answer. He rushed back to write it down. Higgs was not alone. A handful of other scientists were circling the same strange idea at the same time, working in different countries, unaware of each other. But the picture they built together was the same, and it was breathtaking. Their idea went like this: empty space is not truly empty. Woven through every inch of the universe sits an invisible field, a kind of silent ocean with no edges. It fills the space between galaxies. It fills the space inside your body. It was here before the first star, and it is here right now, in the room where you are listening. This field became known as the Higgs field. On its own, the field does nothing you could ever notice. It has no glow, no sound, no weight you can weigh. For centuries it hid in plain sight, because there was no way to feel it. Yet according to the math, this quiet ocean holds the answer to why anything is heavy. The trick is in how particles move through it. Some particles barely feel the field. They slip through it clean and fast, the way a needle slides through water. Those particles stay light or massless, and they zip along near the speed of light. Photons, the pieces of light, are like this. They ignore the field completely, so they fly free forever. Other particles get gripped by the field. They cannot glide, they drag. And the harder the field grips a particle, the more it fights to move, the more stubborn it becomes. That stubbornness, remember, is mass. A particle that the field grabs tightly ends up heavy. A particle the field barely touches ends up light. Suddenly the broken theory healed itself. The particles could stay massless at their core, keeping the beautiful math intact. Their weight came from outside, from their struggle through the invisible ocean. The splinter slid out at last. It was elegant, it was bold, and for a while, it was only an idea on paper, impossible to test. Because how do you prove an invisible field exists when it makes no light, no sound, and no sign at all? How do you catch an ocean that fills everything and shows itself in nothing? Higgs had an answer buried in his math, and it pointed toward one specific, almost impossible target. If you could find that target, you would prove the whole idea true. Let us slow down and really see how the Higgs field hands out mass, because the way it works is stranger and more beautiful than most people ever hear. Imagine a huge swimming pool filled not with water but with thick honey. Now imagine 3 different swimmers about to cross it. The first swimmer is tiny and slippery, shaped like a dart. She barely disturbs the honey. She slides across almost as if the pool were air, reaching the far side in a blink. This swimmer picks up almost no drag, so in the language of particles she stays very light. The second swimmer is broad and clumsy. The honey clings to every part of him. He heaves and strains and crawls across, fighting for every inch. The honey drags on him hard, so he behaves as if he were heavy. In particle terms, this one carries a lot of mass. The third swimmer never touches the honey at all. She floats on top and glides across untouched. That is the photon, the piece of light, which ignores the field and races at full speed forever. The Higgs field works just like that, honey. Every fundamental particle is a swimmer moving through it. How strongly the field grips each particle decides how heavy that particle turns out to be. A weak grip means a light particle. A strong grip means a heavy one. A particle the field cannot grab at all stays massless and flies at light speed. This is why different particles have wildly different weights. The heaviest known fundamental particle outweighs the lightest by hundreds of thousands of times, all because the field grabs one hard and lets the other slip. And here is the part that bends the mind. The particle itself is still nothing on its own. Its weight is a relationship, a constant struggle between the particle and the ocean it swims in. Take away the field, and the weight vanishes. The particle would suddenly weigh nothing and shoot off at the speed of light, unable to ever slow down and build an atom. So the Higgs field does something quietly enormous. It gives the smallest specks of reality the power to stand still. It lets them clump. It lets them settle into atoms. It turns a universe that should have been a blur of weightless light into a place where solid things can exist. That should feel like the answer to everything. If the field gives particles mass, and you're made of particles, then the field gives you your weight, right? That is exactly the leap the headlines made in 2012. It sounds airtight. It even sounds obvious. And it is where the story quietly goes wrong. Because before we can trust any of this, scientists first had to prove the honey pool was really there. They needed to catch a single splash, and that splash had a name. Here is the problem with an invisible ocean. You cannot point at it. You cannot scoop it into a jar. The Higgs field fills all of space and shows itself in nothing you can see. For decades, that made it look untestable, and an idea you cannot test is barely science at all. But Higgs and the others had left a clue in their math, and it was a good one. If the field is truly there, then you should be able to disturb it. Poke a still pond hard enough, and a ripple spreads out. Poke the Higgs field hard enough, they said, and it too should ripple. That ripple would appear in our world as a brand new particle, a little knot of the field itself briefly made solid. They called this ripple the Higgs Boson, so the plan was born. Find the ripple, and you prove the ocean. The Higgs Boson would be a messenger, a single splash that says the whole field is real. There was a catch, and it was brutal. Making that ripple takes a staggering amount of energy crammed into a space smaller than an atom. You cannot poke the Higgs field with your finger. You have to slam particles together so hard that, for the tiniest flash of time, the field trembles and coughs up one boson. That is why they built the giant machine near Geneva, the ring 17 miles around. Inside it, protons race in opposite directions until they move a hair's breadth below light speed, then crash head-on. Each crash packs the energy of a colliding mosquito swarm into a point smaller than anything you can picture. Most crashes give nothing useful. Once in a great while the field ripples, and the Higgs boson does not stick around to be admired. It appears and dies almost instantly, in less time than light takes to cross a single atom. It vanishes into a spray of other particles, so scientists never saw the boson directly. They saw its wreckage, the exact pattern of debris it leaves behind when it dies, like reading footprints in mud left by an animal that already ran off. For years they collided and watched. They counted trillions of crashes. Slowly, in the mountain of debris, a pattern rose above the noise, a bump on the graph that could only come from one thing. In 2012, the bump was solid enough to announce. The ripple was real, therefore the ocean was real. The Higgs field, an idea from a walk in the Scottish hills, had been confirmed by one of the hardest experiments ever run. It was a triumph. Peter Higgs got his tears, the world got its God particle, and almost no one noticed the small quiet sentence hiding in the fine print of the theory. A sentence that shrinks the whole triumph down to something far smaller than the headlines swore it was. Read the theory carefully and you find a line that the celebration skipped right over. The Higgs field gives mass to fundamental particles, the smallest ones, the building blocks that cannot be broken into anything else. That word fundamental is the whole catch. Fundamental particles are the true bottom of reality, the specks that are not made of anything smaller. Electrons are fundamental. The tiny pieces called quarks, which we will meet soon, are fundamental. These are the swimmers in the honey pool, and yes, the Higgs field hands each of them their personal weight. Here is the twist. You are not made only of fundamental particles sitting quietly side by side. You are made of atoms, and atoms are built in layers, and almost all of your weight lives in a layer where the Higgs barely matters at all. Let us do the accounting on your own body. Your atoms are mostly empty space with a heavy core in the middle. That core is where nearly all your weight hides, and that core is not a simple lump of fundamental particles. It is a churning, violent place with its own source of mass, a source that has almost nothing to do with the Higgs field. Think of it this way. The Higgs is like a factory that stamps a tiny weight onto each raw building block. Fine. But when those blocks get slammed together into the core of an atom, something else takes over. Something far bigger starts generating weight out of thin air, and it dwarfs the little stamp the Higgs provided. How much bigger? Hold on to this number, because it is the heart of the whole story. Of all the weight in your body, the part that traces back to the Higgs field is only about 1%. Maybe less. 1%. The God particle, the thing headline said gives everything its mass, is responsible for roughly 1/100th of you. The other 99% comes from somewhere the newspapers never mentioned. It comes from inside the core of every atom, from a storm so violent and so strange that scientists needed a completely different idea to explain it. So the famous story has it backward. The Higgs did not solve where your weight comes from. It solved a small corner of the problem, then left the giant part untouched, hiding in plain sight inside you. If the Higgs gives you only a sliver of your mass, then the real question opens up like a trapdoor. Where does the other 99% actually come from? To find out, we have to shrink down, way down, past the skin, past the cells, into a single atom and then straight into its beating heart. Let us take a journey into your own hand, not the skin you can see, but down and down, into the pieces too small for any eye. Start with your fingertip. Zoom in past the ridges of your print, past the living cells, until you reach a single atom. If that atom were blown up to the size of a football stadium, you would find something eerie. Almost all of it is empty. Row after row of empty seats, silent and dark. Way out at the edges, where the higher seats would be, a few tiny specks race around in a blur. Those are the electrons, and they are fundamental particles, so the Higgs field really does give them their weight. Good for the Higgs. But here is the shock. Electrons are so light they barely count. Add up every electron in your body, and you get less than 1/1000th of your total weight. So the electrons, the particles the Higgs clearly handles, are almost nothing on the scale. Where is all the weight then? Back to the stadium. Down at the very centre, where the field would be, sits a single grain of sand. That grain is the nucleus, the core of the atom. It is unbelievably tiny compared to the whole, thousands of times smaller than the space around it. Yet that lonely grain holds more than 99% of the atom's entire mass. Let that scale sink into your bones. The atom is a stadium of empty seats, and all the weight is 1 grain of sand at the 50-yard line. You, your bones, this planet, everything solid you have ever touched is basically empty space wrapped around tiny, impossibly heavy cores. When you knock on a table and it feels solid, you are not feeling stuff. You are feeling the electric push between electrons, holding your hand out of all that emptiness. The table is mostly nothing, and so are you. So the mystery of your weight has narrowed to one place. The grain of sand, the nucleus, crack that open, and we crack the secret of where 99% of you comes from. The nucleus is built from particles called protons and neutrons, packed together like a tight clump of berries. And this is exactly where the Higgs story quietly dies. Because the weight of a proton, it turns out, is a magic trick. The pieces inside it barely weigh anything, yet the proton as a whole is heavy. Somehow a proton weighs far more than the sum of its parts. Add up everything inside it and you fall drastically short. The rest of the weight appears from nowhere, conjured out of pure energy by the most powerful force in all of nature. To understand that trick, we have to do the unthinkable. We have to break open a single proton and look at the storm raging inside. Reach into the nucleus and pull out one proton. Hold it in your imagination. This is one of the little berries in the clump, one of the building blocks of every atom in your body, and it is about to make no sense at all. For a long time, scientists pictured the proton as a solid ball, a neat little marble of matter. Simple. Then they started firing tiny probes at it, shooting electrons straight into protons to see what bounced back, like throwing pebbles into fog to map what is hidden inside. What they found was not a marble, it was a crowd. Inside the proton sit three main particles called quarks. Quarks are fundamental, the true building blocks, so at last we are back to particles the Higgs field can touch. The Higgs gives each quark its own weight, just as the theory promised. So surely you think the weight of the proton is just the weight of its three quarks added up. Now comes the number that stuns even physicists who have known it for years. Take those three quarks and weigh them alone. Add them together. They account for barely 1% of the proton's total mass. Barely 1%. Read that again. The proton is heavy. It carries almost all the weight of every atom in the universe, and the actual particles inside it, the parts the Higgs field so proudly gives mass to, make up only 1/100th of that weight. It is like weighing a full grocery bag on a scale, then weighing everything inside the bag by hand, and finding that the contents weigh almost nothing. The bag reads heavy. The stuff inside reads empty. Where did the weight come from? This is the moment the whole God-particle story collapses. If the quarks are only 1% of the proton, and the proton is basically all of your weight, then the Higgs field is responsible for only a sliver of you. The rest, that missing 99%, is generated by something else entirely. Something happening in the space between the quarks, because the proton is not calm, far from it. That space between the three quarks is the most violent, energetic place we know of at this scale. It roars, it boils, it is packed with energy so intense that the energy itself becomes weight. To see how energy can turn into weight, we have to bring in the most famous equation ever written and finally understand what it truly means. Not as a line in a textbook, but as the actual factory building most of your body, right now, inside every atom you own. Let us go inside the proton and stay a while, because this place is unlike anything in your daily world. Picture 3 fireflies trapped in a jar. Those are the quarks. They are small, and on their own they weigh almost nothing, as we just saw. But the jar is not calm air. The jar is filled with a raging storm. Binding those 3 quarks together is a force so strong it earned a blunt name. Scientists call it the strong force, because it is the most powerful force in all of nature, far mightier than gravity or the pull of magnets. And the strong force does its work using its own special particles, tiny carriers that fly between the quarks and hold them together. These carrier particles are called gluons, because they act like glue. Gluons stream back and forth between the quarks in a blur, a constant crossfire, thousands upon thousands of them flashing into being and vanishing again every instant. The inside of a proton is a boiling sea of gluons, thick and wild, snapping between the 3 quarks like lightning trapped in a bottle. Here is what makes it dizzying. All that gluon activity carries energy, enormous energy. The storm never rests, never cools, never slows down, and energy, as we're about to see, is not weightless. Energy has weight. The furious boiling energy of that gluon storm is where almost all the proton's mass comes from. So the proton is heavy for a reason that has nothing to do with heavy parts. The parts are nearly weightless. The proton is heavy because of the sheer energy of the battle raging inside it, the endless storm of the strong force holding 3 tiny fireflies in place. Try this comparison. Imagine 3 feathers tied together with unbreakable rubber bands, and those bands are stretched and snapping and vibrating with wild energy, storing more force than a coiled spring. Weigh the whole bundle and it is heavy. Weigh the feathers alone and they are nothing. The weight lives in the tension, in the stored energy of the bands. That is a proton. 3 near weightless quarks, and a storm of binding energy that makes up the rest. This flips everything you were taught. Weight does not have to come from heavy stuff. Weight can come from pure energy, if that energy is packed and trapped tightly enough. Inside every proton, in every atom, in your bones and blood and brain, energy is being frozen into weight this very second. And the 99% of you that does not come from the Higgs, it comes from here, from the energy of the strong force, from the storm. But saying energy becomes weight is a strange claim. It sounds almost like magic. How can something with no substance, pure motion and force, turn into solid mass you can weigh? The answer was written down more than 100 years ago by a man with wild hair, in an equation so short a child can memorize it, and so deep that most people never grasp what it truly says. Everyone has seen the equation. It is on posters, on shirts, scribbled in movies whenever someone wants to look smart. E equals mc squared. Einstein wrote it in 1905 and most people can recite it without having any idea what it means. Let us finally crack it open, because inside this little equation lives the factory that builds almost all of your weight. The equation says something that should stop you cold. Energy and mass are the same thing, wearing different clothes. The E stands for energy, the M stands for mass. They are linked, which means one can turn into the other. Pour in enough energy, and it can freeze into mass. Break apart mass, and it can burst back into energy. The c in the equation is the speed of light, and it is multiplied by itself, which makes it an almost unimaginably huge number. That huge number is the exchange rate between energy and mass. It tells you that a tiny amount of mass is worth a monstrous amount of energy, which is why a single nuclear bomb converting a speck of matter can level a city. But run the equation the other way, and you get the secret of the proton. If a large amount of energy sits trapped in one tiny place, it starts to behave like mass. It gains weight. It resists being pushed, exactly like the stubborn cannonball from before. Energy that is bottled up and going nowhere shows up on a scale as solid weight. Now return to the proton. Inside it, the storm of gluons and the fury of the strong force hold a huge amount of energy, all crammed into a space smaller than you can picture. That trapped energy, following Einstein's equation, turns into mass. It becomes the 99% of the proton's weight that the 3 little quarks could never explain. So the proton is a machine for turning energy into weight. The strong force pours in energy without rest, and Einstein's equation converts that energy into the mass that builds every atom. Your body is running this factory in trillions upon trillions of protons at once, every moment of your life. Sit with how deep that goes. Most of what you call your weight is not stuff at all. It is trapped energy, frozen into the appearance of matter by the fastest speed in the universe. You are, in a real and measurable way, mostly locked up sunlight and fury, held still inside your atoms. The Higgs gives the quarks their tiny masses, yes, but Einstein's equation, powered by the strong force, gives you almost everything else. 2 different sources of weight, and the smaller, quieter one is the one the world crowned the God particle. So the real hero of your mass is this strong force, this storm inside the proton. And it behaves in ways so bizarre that it breaks the simple rules you think you know about how forces work. Because the strong force does something no other force in nature would dare to do. We keep saying the strong force is the most powerful in nature. Let us actually meet it, because it plays by rules that sound almost impossible. Every other force you know gets weaker with distance. Gravity fades the farther you drift from a planet. Magnets lose their grip as you pull them apart. Move away from the source, and the pull dies down. That is how forces are supposed to behave. The strong force does the opposite, and this is the strange heart of it. The farther you try to pull 2 quarks apart, the harder the force yanks them back. Up close, quarks can drift around fairly freely, like two dogs on a very loose leash, but start pulling them apart and the leash does not stretch and weaken. It grows tighter and stronger the more you pull, until it fights back with unbelievable power. Picture a rubber band between two quarks. Nudge them a little and the band is slack, easy. Pull them apart and the band stretches, and the tension climbs, and it never lets up. Ordinary rubber snaps when stretched too far. This band does not snap. It just keeps getting stronger, storing more and more energy the wider you stretch it. This is why the strong force can pump so much energy into the proton. The quarks are locked in these unbreakable, ever-tightening bands, and the bands hold immense stored energy, and that energy, through Einstein's equation, becomes the mass of the proton. The strong force is basically a machine for cramming energy into a tiny space and refusing to let it out. And it leads to one of the wildest facts in all of physics. You can never ever pull a single quark out of a proton to look at it alone. Nobody has done it. Nobody ever will. The rules of nature forbid it. Here is what happens if you try. Say you grab one quark and pull with everything you have, stretching that band tighter and tighter, pouring in more and more energy. At some point, the energy in the stretch band gets so huge that Einstein's equation kicks in hard. The trapped energy converts into brand new particles. Fresh quarks pop into existence out of the pure energy of the strain. So instead of ending up with one lonely quark in your hand, you end up with new quarks appearing to pair off with the old ones. The proton simply refuses to give up a solo quark. Try to isolate one, and the universe spends the energy to build more rather than let a quark go free. Scientists gave this bizarre lockdown a name. They call it confinement, because quarks are confined, forever trapped inside their little storms, never to roam alone. It is one of the strangest rules in nature, and it holds without a single known exception. So the strong force builds your weight, and it does so through a rubber band that never snaps, and a prison that no quark can escape, a place where energy turns into new matter the moment you push too hard, which raises a question that turns the whole picture even stranger. If pulling quarks apart creates new particles, then what is really going on inside the proton moment to moment? The answer is a scene wilder than anything so far. Let us go back inside the proton one more time, now that we know its secrets, and watch what is truly happening in there. Because it is one of the most chaotic scenes in the entire universe, and it is inside every atom of you. You might still picture 3 quarks sitting calmly with some gluons flying between them. Throw that picture away. The reality is a boiling, screaming frenzy. Inside the proton, particles are flashing into existence and vanishing again constantly, trillions of times faster than you could ever count. The strong force is so packed with energy that the space itself keeps coughing up temporary particles. Extra quarks appear in matched sets, live for the briefest flicker, then vanish back into the energy they came from. Gluons pour out gluons of their own, spawning more storm from the storm. The whole interior churns like a pot of water boiling so hard it becomes a blur. Physicists have a name for these flickering, short-lived particles. They call them virtual particles, because they wink in and out too fast to grab, borrowing energy for an instant and paying it back before the universe notices. At any moment, the proton is not 3 quarks. It is 3 quarks lost inside a raging crowd of countless others, all appearing and dying in a frenzy. Try to picture it. Imagine a calm pond. Then imagine a downpour so violent that the surface is nothing but exploding droplets and spray. A chaos so thick you cannot tell water from air. Now shrink that storm smaller than an atom and make it never stop. Not for a billionth of a second. Not since the universe began. That is the inside of a single proton. That is what you are made of. And all of that churning, all of that flashing energy is exactly what weighs so much. The mass of the proton is the mass of the storm. Every flickering particle, every stretched gluon band, every burst of borrowed energy adds to the weight, all of it frozen into mass by Einstein's equation. So your body is not calm at all deep down. In every proton, in every atom, this violent storm rages without pause. Your bones are storms. Your blood is storms. The chair you sit on is storms. Reality, at its heart, is a churning ocean of energy pretending to be solid stuff and doing a very convincing job. This is the true answer to where your weight comes from. Not a quiet field handing out mass. A screaming storm of the strongest force in nature, trapped inside particles that can never break free, turning raw energy into the illusion of solid matter, moment after moment, forever. And now we can finally weigh the Higgs against the storm and see, honestly, how much of you each one built. The answer is going to feel almost unfair to the particle the whole world crowned. Time for the honest reckoning. Let us line up the two sources of your weight side by side and see the truth the headlines hid. On one side stands the Higgs field, the famous God particle. Its job is real and important. It gives the fundamental particles their own personal masses. It gives the electron its weight. It gives each quark its own small weight. Without the Higgs, those particles would be massless and would blast apart at light speed, and no atom could ever form. The Higgs makes atoms possible. That is a genuine gift, and it earns the field its place in history. On the other side stands the strong force and the storm inside the proton, converting energy into mass through Einstein's equation. This is the source that builds the crushing majority of your weight. Now, the tally. Take your whole body and ask how much of its mass traces back to each source. The Higgs, through the tiny masses it gives the quarks and electrons, accounts for roughly 1% of you. The storm of the strong force, freezing energy into weight, accounts for the other 99%. For every pound of you, something like 1/5 of an ounce comes from the Higgs. The rest is trapped energy. So the God particle, the thing newspapers said gives everything its mass, actually gives you about 1/100th of your weight. The real heavy lifting, the 99 parts out of 100, comes from a force most people have never even heard named. Think of building a house and giving all the credit to the person who supplied the doorknobs, while ignoring the crew that poured the entire foundation, raised every wall and built the whole structure. The Higgs supplied something small and necessary. The strong force built the house. This is why saying the Higgs solved the mystery of mass is so misleading. It solved a narrow, specific puzzle, why fundamental particles have weight at all. It answered that beautifully. But the everyday question, why you weigh what you weigh, was answered by Einstein and the strong force long before the Higgs was ever found. The famous discovery in 2012 confirmed a small correction to a story that was mostly written already. The Higgs is not a fraud. It is a real, confirmed, vital piece of nature. But its nickname wrote a check its actual job cannot cash. It is a minor contributor to your mass wearing the crown of the main event. And here is the twist that keeps the story going. Even in its own small corner, even for the tiny job it does have, the Higgs is riddled with problems that physicists cannot explain. The 1% it handles opens up puzzles so deep they threaten to break physics all over again. Because the moment you ask why the Higgs field is as strong as it is, the whole thing starts to wobble in a way nobody can fix. So the Higgs gives fundamental particles their weight. Fine. But that just pushes the mystery back a step and asks a harder question. What decides how strong the Higgs field is in the first place? Remember, the field grips each particle with a certain strength, and that grip sets the particle's mass. The overall strength of the field, then, is a deeply important number. Turn it up, and every particle gets heavier. Turn it down, and everything gets lighter. Turn it off, and mass vanishes and atoms fall apart. So the strength of the Higgs field is one of the most important numbers in all of reality. And when physicists tried to calculate what that number should be, they got an answer so wrong it broke their brains. Here is the trouble. The Higgs field sits in space, and space, as we saw, is a churning storm of virtual particles flickering in and out. All of those flickering particles tug on the Higgs field. Every one of them adds its own little push to the field's strength. When physicists add up all those pushes, the math says the Higgs field should be crushingly, monstrously strong. Not a little strong, astronomically strong. The calculations say the Higgs field should be something like 10,000 trillion times stronger than what we actually measure. If that were true, every particle would be unimaginably heavy. and the universe as we know it could never exist. Yet the real Higgs field is featherlight compared to that prediction. It sits at a gentle, modest strength, exactly the value needed for atoms and stars and people to exist. The math screams that it should be enormous. Reality shows it to be tiny. The gap between prediction and truth is one of the widest and most embarrassing in all of science. Picture a scale built to weigh mountains, and you place a single feather on it, and somehow the needle reads the exact weight of that feather perfectly, even though the scale should have been slammed to its limit by 1,000 invisible boulders piled on top. For the feather to read right, every one of those boulders would have to be cancelled out by an equal and opposite weight, matched to a mind-bending number of decimal places. That is the situation the Higgs field is in. Physicists call this the fine-tuning problem, and it haunts them. For the Higgs to come out as light as it does, a huge pile of enormous pushes has to cancel out almost perfectly, leaving only a tiny remainder. The universe looks balanced on a knife edge, tuned to impossible precision for no reason anyone can find. Either that perfect balance is a staggering coincidence, or something deep and hidden is forcing it to happen. And a coincidence that precise makes scientists deeply uneasy. There should be a reason. The search for that reason sent physicists hunting for a whole hidden half of the universe, an entire family of undiscovered particles that could make the math balance naturally. They were so sure they would find them, and what happened next shook the field to its core. If the Higgs field should be monstrously heavy, yet somehow comes out featherlight, physicists needed a reason, a mechanism, something that cancels out all those enormous pushes and leaves the field gentle. And in the 1970s, they dreamed up an answer so elegant that almost everyone fell in love with it. The idea was called supersymmetry. The logic went like this. All those virtual particles pushing the Higgs field toward monstrous strength come in two basic types, and the two types push in opposite directions. One type shoves the field up, the other type pulls it down. In our known list of particles, these two teams are lopsided, so they do not cancel, and the math blows up. But what if every particle we know has a hidden partner, a secret twin on the opposite team? Then every upward push would be matched by a downward pull from its twin. The enormous numbers would cancel almost perfectly, and the Higgs field would come out light for a real reason, not by dumb luck. The knife-edge balance would finally make sense. It was gorgeous. Supersymmetry did more than fix the Higgs. It hinted at deeper unity in the laws of nature, and it even offered a possible explanation for other cosmic mysteries. Whole careers were built on it. Textbooks were written. Physicists were so confident that the partner particles existed that many treated it as nearly certain. When they switched on the giant machine near Geneva, catching the Higgs was one goal. Finding these hidden twins was the other, and plenty of scientists thought the twins would be the bigger prize. Then the machine ran, and ran, and ran for years at higher and higher energies, searching every corner where the partner particles should have been hiding. They found nothing. Not one partner particle appeared, not a whisper. The places the twins were supposed to live turned up empty, over and over. The most beautiful idea in decades, the elegant fix for the fine-tuning problem, showed no sign of being true. The silence where the twins should have shouted grew louder every year. This was a quiet earthquake. If supersymmetry is wrong or hiding far out of reach, then the fine-tuning problem stands wide open with no clean solution. The Higgs field is light, impossibly light, and the best explanation anyone had built for why is missing in action. Physicists are still reeling from that silence. Some think the twin particles are just heavier than the machine can reach, waiting for a bigger collider. Some think the whole idea is simply wrong, and nature does something else entirely. Some are staring into stranger possibilities, wondering if our universe is balanced on that knife edge by pure chance among countless other universes we can never see. So even the 1% of your mass that the Higgs handles rests on a mystery no one has cracked. The field is here, it works, and nobody knows why it is as gentle as it is. But the trouble does not stop with the Higgs itself, because there are particles pouring through your body right now by the trillions that the plain Higgs recipe was never even able to explain. Ghost particles that should have weighed nothing at all. Right now, as you listen, Trillions of tiny particles are passing straight through your body, through your eyes, your heart, your bones, without touching a thing. They pass through the entire Earth as if it were an open window. They are called neutrinos, and they are the ghosts of the particle world. Neutrinos are almost impossibly shy. They barely interact with anything. You could send a neutrino through a wall of solid lead stretching for miles, and it would sail out the other side untouched. Trillions from the sun pass through your fingernail every second, day and night, and you never feel one. They are the most numerous particles with mass in the universe, and they are also the most invisible. For a long time, scientists thought neutrinos weighed exactly nothing. Zero mass, massless, like light. The great theory of particles, the same beautiful math we met at the start, was built assuming neutrinos had no mass at all. And the Higgs recipe fit that assumption neatly. The field simply never gripped the neutrino, so the neutrino stayed weightless and flew at nearly the speed of light. Clean and simple. Then experiments deep underground caught the neutrinos doing something impossible for a massless particle. Neutrinos come in 3 types, 3 flavors. Scientists watched neutrinos stream in from the sun and from the sky, and they noticed the particles were changing flavor in mid-flight, morphing from one type into another as they traveled. A neutrino that started as one kind would arrive as a different kind. This shape-shifting, called oscillation, carries a hidden rule buried in the physics. A particle can only change flavor in flight if it has mass. Massless particles cannot do it. Full stop. So the neutrinos had to have mass. Tiny, but real. The discovery was so important it won a Nobel Prize, and it rewrote a piece of the rulebook that everyone had thought was settled. Here is why that shook things. The simple Higgs recipe had no natural way to give the neutrino its weight. To make it work, physicists had to bolt on awkward extra pieces or invent new kinds of particles nobody has ever seen. The neutrino's mass is so absurdly small, millions of times lighter than the electron, that it looks nothing like the masses the Higgs hands out to other particles. It feels like it came from somewhere else, through some door the plane theory never had. Picture a recipe that perfectly explains how to bake every cake in the shop, and then one day a strange feather-like cake appears that the recipe cannot account for at all. You did not expect it. Your instructions do not cover it. Something outside your cookbook made it. That is the neutrino, a ghost that was supposed to weigh nothing, caught red-handed carrying a whisper of mass the Higgs cannot cleanly explain. It is a crack in the theory, a sign that our picture of mass is missing pieces we have not found. And the neutrino is only the beginning of what the Higgs leaves out, because when astronomers looked out at the whole universe and weighed it, they found that most of the weight out there is made of something the Higgs field has never even touched, something invisible, enormous, and completely unknown. Step outside on a clear night and look up. Every star you see, every planet, every cloud of gas glowing between them is made of the same stuff you are. Atoms, protons full of storms, all of it built from the pieces we have been tracing. Now here is the gut punch. All of that visible matter, every glowing thing in the sky, makes up only about 1/6 of the actual weight in the universe. The rest is invisible. Astronomers can measure it. They can feel its pull, but they cannot see it, touch it, or catch it. They call it dark matter, and there is roughly 5 times more of it than all the stars and planets and people combined. How do we know something invisible is even out there? Scientists watched how galaxies spin. A galaxy is a giant pinwheel of stars turning slowly in space. By the rules of gravity, the stars at the outer edge should whip around slower than the ones near the middle, the way the outer horses on a merry-go-round should lag behind. But they do not lag. The outer stars race around just as fast as the inner ones, as if something heavy and unseen were wrapped around the whole galaxy, gripping it together. There was not enough visible matter to explain that grip. Not even close. So either gravity works differently than we think, or the galaxies are packed with enormous amounts of invisible weight we cannot see. The evidence kept piling up, from spinning galaxies to bent starlight to the afterglow of the early universe, and it all pointed the same way. Something massive is out there in the dark, holding everything together. So most of the weight in the whole universe is made of a substance nobody has ever identified. And now comes the part that matters for our story. The Higgs field says nothing about it. Remember, the Higgs gives mass to the fundamental particles we know: electrons, quarks, the building blocks of ordinary matter, but dark matter is not made of any of those. Whatever it is a new kind of stuff, outside the whole list of particles the Higgs field handles. The famous God particle, crowned for giving everything its mass, does not even touch 5/6 of the mass in existence. Picture being handed the bill for a massive banquet and being told you only have to explain the cost of the napkins. Ordinary matter, the only thing the Higgs helps with is a rounding error compared to the dark matter filling the cosmos. The Higgs explains the napkins. The feast remains a total mystery. This is one more crack in the idea that the Higgs solved the problem of mass. It handles a thin slice of ordinary matter, gives most of that slice only a tiny fraction of its weight, and has nothing at all to say about the invisible bulk that outweighs everything we can see. Which leaves an obvious and burning question hanging in the dark. If dark matter is real, and there is 5 times more of it than everything else, then what is it made of? And does it feel the Higgs field at all? Or is it deaf to the very thing that gives ordinary matter its weight? The honest answer is stranger than the question. So what is dark matter actually made of? Here is the humbling truth. After decades of searching, with detectors buried in mines and machines the size of buildings, nobody knows. It remains one of the biggest unsolved puzzles in all of science. We know a few things about it, and they are strange. Dark matter has weight, because it pulls on galaxies with gravity, but it seems to ignore almost everything else. It gives off no light, which is why it stays invisible. It passes through ordinary matter like a breeze through a screen door. Right now, a river of dark matter is very likely flowing straight through your body and through the entire planet, and you feel nothing. Scientists have a leading guess. They think dark matter might be a brand new kind of particle, one we have never caught, drifting through the universe in vast clouds. These would be particles that carry weight but barely interact, ghosts even shyer than the neutrinos we met earlier. They have hunted for these particles for years, building ultra-sensitive detectors deep underground, waiting for even a single one to bump into an atom. So far, the detectors have stayed silent. Search after search comes up empty. The particle everyone expected to find keeps not showing up, which has physicists wondering if dark matter is something even weirder than they imagined. And now the question that cuts to the heart of our story. Does dark matter get its weight from the Higgs field, the same way ordinary particles do? The plain answer is that we have no evidence it does. If dark matter is a new particle, it might get its mass from the Higgs field, or it might get its mass from some completely different source we have not discovered. It could be tied to a whole hidden sector of physics with its own rules, its own forces, maybe even its own version of a Higgs field that has nothing to do with ours. Some scientists suspect dark matter barely notices our Higgs field at all. If that is true, then the mechanism that gives ordinary matter its mass is simply irrelevant to the majority of matter in the universe. The Higgs would be a local rule, one that governs our familiar particles while the cosmic majority follows laws we have not even glimpsed. Think of it like discovering that the language everyone speaks in your town is spoken by only a tiny fraction of the world, and the vast majority of people out there use a language you have never heard, with an alphabet you cannot read. The Higgs might be our town's language. Dark matter might be speaking something else entirely. This is why physicists get uneasy when the Higgs is called the source of all mass. It handles the mass of a minority of matter, and even for that minority it supplies only a sliver. The enormous dark portion of the universe sits outside its reach, keeping its secrets, and dark matter is only part of the missing picture. Because when scientists measured the total energy of the universe, they found that even dark matter and ordinary matter together are outweighed by something else. Something stranger still, hiding in the emptiest emptiness there is. It lives in the vacuum itself, in the space that looks like pure nothing. We keep calling empty space empty. A vacuum. Nothing there. No air, no light, no matter, just a clean void. That picture feels obvious, and it is completely wrong. Empty space is one of the busiest places in the universe. Remember those virtual particles from inside the proton, the ones flickering in and out of existence, borrowing energy for an instant and vanishing again? They do not only happen inside protons, they happen everywhere, in the gap between stars, in the space inside an empty box, in the room around you right now, even in a perfect vacuum with every atom removed, particles keep boiling into being and disappearing, trillions of times over, filling the void with a constant fizz of activity. This means empty space is not still and dead. It carries energy. The vacuum itself hums with the energy of all those flickering particles, and by Einstein's equation, the one that turns energy into weight, that vacuum energy should carry mass too. Space itself, the pure nothing between everything, has a weight built into it. For most of history, nobody could have imagined this. Then astronomers made a discovery that turned the vacuum from a curiosity into the deepest crisis in physics. They were watching distant galaxies to measure how the universe was expanding. Everyone assumed the expansion was slowing down, dragged on by the gravity of all the matter pulling inward. It made sense. Throw a ball up and gravity slows it. Push the universe outward, and gravity should slow that too. They found the opposite. The universe is speeding up. Galaxies are flying apart faster and faster, as if some invisible pressure were pushing space itself to stretch harder every year. Something is shoving the cosmos outward against the pull of all its gravity and winning. Scientists name this pushing force dark energy, and when they added up how much of it there is, the number was staggering. Dark energy makes up close to 70% of everything in the universe. Not 70% of the matter, 70% of the total, more than dark matter and ordinary matter put together. So here is the full picture at last. The universe is mostly dark energy, spread through the vacuum, pushing everything apart. A big chunk of the rest is dark matter, invisible and unknown, and the tiny remainder, a few percent, is the ordinary matter that makes up stars and planets and you. That few percent is the only part the Higgs field has anything to do with, and even there it supplies a fraction. The God particle governs a corner of the cosmos. Now, dark energy looks a lot like that vacuum energy, the weight built into empty space by all those flickering particles. So maybe physics already has the answer. Maybe dark energy simply is the energy of the vacuum. That would be a beautiful solution. Except when scientists calculated how much energy the vacuum should hold, and compared it to how much dark energy they actually measured, they got the worst mismatch in the entire history of science. A wrong answer so enormous that physicists talk about it with a kind of horror. It is called the worst prediction ever made, and the size of the error is almost impossible to say out loud. Let us look at the worst prediction in the history of physics, because the numbers involved are so absurd they almost stop meaning anything. The setup is simple. Empty space fizzes with energy from all those flickering virtual particles. Physicists can calculate how much energy that should add up to. They can also measure how much dark energy is actually out there, pushing the universe apart. If the vacuum energy is the dark energy, the two numbers should match. They do not match. The prediction is too big, and when scientists say too big, they mean it in a way that breaks the mind. The calculated vacuum energy is larger than the measured dark energy, by a number that has more than 100 zeros after it. Written out, it is 1 followed by roughly 120 zeros. There is no comparison in daily life that can hold a number that size. It is vastly more than the count of every atom in every star and every galaxy in the entire visible universe. So physics did its best calculation of the energy in empty space, and the answer was wrong by a factor with over 100 zeros. If the calculation were right, the vacuum energy would be so ferocious that it would have ripped the universe apart instantly after the beginning, tearing every atom to shreds before a single star could form. You would not exist. Nothing would. Yet here we are, in a calm, slowly expanding universe, with a dark energy so gentle it took astronomers until recently to even notice it. The real number is tiny. The predicted number is monstrous. The gap between them is the largest error ever produced by a serious scientific theory. Physicists gave this catastrophe a name. They call it the cosmological constant problem, and many consider it the deepest, most embarrassing unsolved puzzle in all of physics. It sits there like a crack in the foundation of everything, and nobody has a solid explanation for why the vacuum energy is so gentle when the math screams it should be overwhelming. Picture an engineer calculating how much a bridge will weigh and getting an answer so large it should collapse into the centre of the earth, and then walking outside to find the bridge standing there, light as a feather, holding perfectly. That is where physics stands with the energy of empty space. The theory and the reality disagree by an amount too big to picture. Now connect this back to our story. This vacuum energy comes from the same restless quantum fizz that also tries to inflate the Higgs field to monstrous strength. The same flickering particles that push the Higgs toward being crushingly heavy also push the vacuum toward being violently energetic. In both cases, the universe somehow comes out gentle and mild, tuned to an impossible degree of precision for reasons no one can find. Two of the deepest numbers in reality, the strength of the Higgs field and the energy of the vacuum, both sit at values so delicately balanced that they look almost hand-picked to allow a universe like ours, and nobody knows why. So the Higgs is tangled up in mysteries far bigger than itself. It cannot even keep its own strength stable without a cosmic balancing act. And it turns out the Higgs plays one more trick that scientists still barely understand, one that loops back on the particle in the strangest way of all. Here is a fact about the Higgs that sounds like a riddle. The Higgs boson gives mass to other particles, but it also gives mass to itself. Let that strangeness settle for a moment. Every other particle we have discussed gets its mass by interacting with the Higgs field from the outside. The electron pushes through the field and gains weight. Each quark pushes through and gains weight. The field is the source, the particles are the customers. Simple enough, but the Higgs boson is a ripple of the Higgs field. So when the Higgs boson moves, it is moving through its own field. It interacts with itself. The Higgs gives the Higgs its weight. It is a particle that holds itself up by its own bootstraps, a snake that feeds on its own tail. This self-interaction is real, and it is a core part of the theory. The Higgs field talks to itself, tugs on itself, and that self-conversation shapes how the whole field behaves. It decides the strength the field settles into, the very strength that determines every particle's mass. So this loop, the Higgs acting on itself, sits at the foundation of the entire mass-giving machine. And here is the uncomfortable part. It is the piece scientists understand least of all. When the Higgs was discovered in 2012, physicists confirmed the field exists and confirmed it gives mass to other particles. They measured how strongly the Higgs grips electrons and quarks. But they have barely been able to test how strongly the Higgs grips itself. That self-interaction is fiendishly hard to measure. It takes collisions so rare and so precise that the giant machine near Geneva has only just begun to glimpse it. Why does this matter so much? Because the self-interaction of the Higgs controls the shape of the field, and the shape of the field decides the fate of the universe. Imagine a ball resting at the bottom of a valley. That resting spot is the strength the Higgs field has settled into, the comfortable value that gives us the masses we see. The shape of the valley, how steep its walls are, how deep the bottom sits, is set by how the Higgs interacts with itself. Measure that self-interaction, and you learn the true shape of the valley the universe is resting in. And that shape holds a secret that is either reassuring or terrifying, depending on what we find. Because the ball at the bottom of the valley might be sitting in the lowest, safest point there is, or it might be perched in a shallow dip, with a far deeper valley hidden somewhere beyond, waiting. If the Higgs field is resting in a false bottom, then everything we know is balanced above a cliff we cannot see. The stability of every atom, every star, every law of physics could depend on the exact shape of a valley that scientists have only started to measure. So the least understood feature of the Higgs, its quiet conversation with itself, may decide whether our universe is safe or living on borrowed time. To understand how that could be, we have to go back to the very beginning, to the instant the Higgs field first switched on and gave the young universe its weight. Rewind the universe. All the way back to the first tiny fraction of a second after everything began. The cosmos is unimaginably hot, a searing fireball far hotter than the centre of any star. And in that furnace, something surprising is true. The Higgs field is switched off. At those blazing temperatures right after the beginning, the Higgs field had no strength at all. It did not grip particles. It did not hand out mass. So every fundamental particle in the early universe was massless, all of them racing around at the speed of light, unable to slow down, unable to clump, unable to build a single atom. The whole young cosmos was a blur of weightless particles moving as fast as anything can move. For that first sliver of time, mass did not exist. The universe was a storm of pure, weightless speed. Then the universe expanded, and as it expanded, it cooled. Like steam cooling into water droplets, the cosmos passed through a critical temperature, and at that instant something switched. The Higgs field, which had been sitting at zero, suddenly turned on. It flooded space with its strength. It began gripping particles, and in that moment, everywhere at once, the fundamental particles gained their mass. Scientists call this moment the electroweak transition. It happened a tiny fraction of a second after the beginning, and it was one of the most important events in the history of everything. Before it, a universe of massless light. After it, a universe where particles have weight, where they can slow down, where they can eventually gather into atoms and stars and galaxies and you. Think of it like a stadium full of people suddenly stepping into wet concrete that flash sets around their feet. One instant they are running free, the next instant they are gripped, weighted, slowed, held in place. That switch, from free to gripped, is what happened to every particle in the universe when the Higgs field turned on. So the Higgs field was not always doing its job. It has an origin, a moment it came online, and everything solid in existence traces back to that instant. In a real sense, mass has a birthday, and it is written into the earliest history of the cosmos. This is a genuine achievement of the theory, and it deserves respect. The idea that the Higgs field switched on in the early universe fits beautifully with what we understand about how the cosmos cooled and grew. It is one of the places where the Higgs story works exactly as it should. But it also opens a chilling door, because if the Higgs field switched on once, settling into the strength it has today, then a question follows that keeps some physicists up at night. Is the strength it settled into permanent? Is it locked in forever? Or could the field, under the right conditions, switch again and settle into a completely different value? If it could switch again, the results would rewrite reality. And before we face that possibility, there is another gap in the Higgs story we have to confront. Because when the field switched on and handed out mass, it left behind a puzzle it has never been able to explain. It gave particles their weights, but it never explained why those weights come in such a bizarre pattern. When the Higgs field switched on and gave particles their masses, it made a strange choice. It did not give every particle a similar weight. It handed out masses that vary wildly, following a pattern so odd that physicists have puzzled over it for decades. Here is the puzzle. The fundamental particles of matter come in 3 sets, like 3 copies of the same basic family. Scientists call them generations. Everything you are made of belongs to the first generation, the lightest one. Electrons and the 2 kinds of quarks inside protons and neutrons all sit in that first gentle group. But nature built 2 more copies. The second generation holds particles just like the first, with the same charges and behaviours, only heavier. The third generation holds another copy, heavier still. It is as if nature designed one set of building blocks, then made 2 more versions of the exact same set, each one weighing far more than the last, for no reason anyone can find. The weight differences are enormous. The heaviest fundamental particle, a giant quark in the third generation, outweighs the lightest quark in the first generation by roughly 100,000 times. Same type of particle, same role, wildly different mass. The Higgs field grips one of them almost carelessly and grips the other with crushing force, and nothing in the theory explains why. This is one of the quiet failures of the Higgs story. The Higgs field is the machine that hands out these masses, but it does not decide their values. Those values are just fed into the theory by hand, measured from experiments and typed in. The Higgs tells you that particles get mass by gripping the field. It never tells you why the electron gets such a feather-like grip while its heavy cousin gets slammed. Imagine a factory that stamps a weight onto every product, but the weights follow no rule at all. One item comes out light as paper. The next, identical-looking item comes out heavy as an anvil. A third weighs somewhere in between. Ask the factory why, and it just shrugs. The machine stamps the weights, but something outside the machine chose the numbers, and nobody can find where those numbers come from. That is exactly the state of the Higgs and the masses. The pattern of particle weights is one of the deepest unsolved riddles in physics. Why 3 generations? Why not 2 or 5? Why do the masses climb so steeply from one generation to the next? The Higgs is silent on all of it, and it gets stranger, because most of these heavier particles do not even exist in the everyday world. The 2nd and 3rd generation particles are unstable. Make one in a collision, and it survives for the tiniest flash before falling apart into lighter particles. The universe built 2 entire families of heavier matter, and then made them so fragile they vanish almost instantly. They played some role in the early cosmos, and now they only appear in the violent crashes inside our biggest machines. So the Higgs gives mass, but it does not explain the masses. It is a rule book missing its most important chapter, and this missing chapter connects to a mystery even larger than the pattern of weights, a mystery about why there is any matter in the universe at all, rather than nothing. Here is a fact that should not be true. You exist. The stars exist. There is matter in the universe. And according to our best understanding of the beginning, there almost should not be. When the universe began, in that first hot instant, energy was busy turning into matter, following Einstein's equation in reverse. Pure energy froze into particles. But there is a rule to how this works, and the rule is strict. When energy turns into matter, it always makes matter and antimatter in equal amounts. Antimatter is the mirror image of ordinary matter. For every kind of particle, there is an antiparticle, a twin with the opposite charge, and these twins have a violent relationship. When a particle of matter meets its antimatter twin, they destroy each other completely, vanishing in a flash of pure energy. Total mutual annihilation. So picture the early universe. Energy pours into matter, making equal amounts of matter and antimatter. Then all that matter and antimatter meets, twin by twin, and annihilates back into energy. If the amounts were truly equal, the story ends there. Everything cancels out. The universe becomes a bath of light with no solid matter left in it. No atoms, no stars, no you. But that is not what happened. Somehow, when the dust settled, a small amount of matter was left over. For every billion pairs of matter and antimatter that annihilated, about 1 extra particle of matter survived, with no twin to cancel it. That tiny surplus, 1 part in a billion, is everything. Every star, every planet, every atom in your body is built from that leftover scrap that escaped annihilation. So there was a slight imbalance in the beginning. Matter beat antimatter by the thinnest margin, and that margin is why anything solid exists at all. Which raises the obvious question. Why? Why was there any imbalance? The rules say matter and antimatter should have been made in perfectly equal amounts. Something tipped the scale, just barely, in favour of matter. And nobody knows for certain what. And here is why this belongs in our story. The Higgs field, the supposed source of mass, has almost nothing to say about it. The Higgs gives particles their weight, but it does not explain why matter won its ancient battle against antimatter. That imbalance came from some other feature of physics, one we have not fully identified. The mechanism that lets you exist at all sites outside the Higgs entirely. Picture 2 vast armies, matter and antimatter, meeting on a battlefield in perfect balance, destined to wipe each other out to the last soldier. And yet when the smoke clears, a single small squad of matter is left standing, alive, with no enemy remaining. That lone surviving squad grew into everything. Why it survived, what secret advantage it held, remains one of the great open questions. So the Higgs gives mass to particles that only exist because of a mystery the Higgs cannot explain. It builds the weight of a universe whose very existence depends on a puzzle beyond its reach. The gaps keep widening, and now we arrive at the deepest gap of all, one so fundamental that it exposes what the Higgs never even attempted to do. Because for all its fame, the Higgs explains one kind of mass while staying completely silent about another. There is a hidden double meaning in the word mass, and it exposes the biggest gap of all in the Higgs story. Because mass does 2 completely different jobs, and the Higgs only helps with one of them. The first job we have already met. Mass is resistance, the stubbornness that fights when you try to push something. Kick a cannonball, break your toe. That is inertial mass, how hard a thing is to get moving, and this is the mass the Higgs field helps create, by gripping fundamental particles and making them hard to shove. But mass does a second job, and it is arguably the more important one. Mass makes gravity. Anything with mass pulls on everything else with mass. The Earth pulls you down. The sun holds the planets. Your body right now is tugging faintly on everything around you. This is gravitational mass, the property that creates the pull we call weight and gravity. Here is the astonishing thing. These two kinds of mass, the stubbornness and the pull, are always exactly equal. Every object resists being pushed by precisely the same amount that it pulls on other things. Drop a bowling ball and a marble from a tower, and they fall at the same rate because each object's stubbornness and its gravity cancel out in perfect step. Scientists have tested this to astonishing precision, and it holds every single time. Nobody fully knows why. It is one of the deepest facts in physics, so deep that the greatest theory of gravity we have is built entirely on top of it. And notice what is missing from all of this: the Higgs. The Higgs field explains inertial mass. It explains why particles resist being pushed. But it says absolutely nothing about gravitational mass. It does not explain why mass creates gravity, why weight pulls, why the stubbornness of a particle should also make it bend the space around it. Gravity is governed by a completely separate theory, one that does not mention the Higgs at all. And these two great theories, the one that includes the Higgs and the one that describes gravity, do not fit together. They are like two beautifully written books in two different languages that refuse to be translated into each other. Physicists have spent lifetimes trying to unite them and keep hitting a wall. The Higgs lives entirely in one book. Gravity lives entirely in the other. Nobody has built the bridge. So the God particle, celebrated for explaining mass, only explains half of what mass even is. It handles the stubbornness. It is silent on the pull. And the pull, gravity, is the force that shapes galaxies, holds stars together, and bends the very fabric of space and time. Picture a locksmith famous for making the finest keys in the world, and then learning those keys only open one type of lock, while the most important doors in the building use a completely different mechanism the locksmith has never even studied. The Higgs opens the lock of inertia. The great door of gravity stays shut. This might be the widest gap of all. The property that governs the entire large-scale universe. The reason planets orbit and galaxies spin has nothing to do with the particle we crowned as the source of mass. And there is a final humbling truth, one that shows just how loosely we grasp even the small part of mass we think we understand. Because the 99% of your weight, the part built by the strong force inside the proton, is so complicated that no human can calculate it by hand. Let us return to the proton, that storm inside every atom that builds most of your weight. We told the story of how it works. 3 quarks, a raging sea of gluons, energy frozen into mass by Einstein's equation. It sounds like we understand it, and in a broad sense, we do. But here is a fact that reveals how loose our grip really is. Nobody can calculate the exact mass of a proton with a pencil and paper. Not the smartest physicist alive. The math is simply too wild. Remember how chaotic the inside of a proton is. Countless particles flickering in and out, gluons spawning gluons, quarks appearing and vanishing, all of it churning trillions of times faster than thought. To calculate the proton's mass, you would have to account for that entire storm, every flickering contribution all at once. The equations that describe it are so tangled that they cannot be solved directly. Pick up a pen and try, and you drown in the complexity before you begin. So how do scientists calculate the proton's mass at all? They cheat in a clever way. They chop space and time into a grid, a bit like the pixels on a screen, and they let some of the most powerful supercomputers on Earth crunch the storm one tiny piece at a time. The computers grind through the calculation for months, simulating the seething interior of a single proton in a giant digital lattice. Only then, after all that machine power, does a number come out, and the number matches the measured mass beautifully. That match is a triumph. It proves we understand the basic rules of the strong force. It confirms that the storm really does build the proton's weight, exactly as the theory says. This is one of the great victories of modern physics. But sit with what it means. The source of 99% of your body's weight is so complicated that it takes some of the largest supercomputers ever built, running for months, just to compute the weight of one proton. One. and you contain more protons than there are stars in the observable universe, many times over. Picture trying to predict the exact path of a single leaf in a hurricane. The rules of wind and air are known, but the storm is so chaotic that even knowing the rules, you need enormous computing power to trace one leaf for 1 second. The proton is that hurricane, shrunk smaller than an atom, and it takes a computer the size of a room to follow it. So even the part of mass we supposedly understand, the strong force part, sits right at the edge of what human minds and machines can handle. We know the rules, we can barely do the arithmetic. The storm inside you is that fierce. This is the real texture of the mass problem. It is deep, it is tangled, and it stretches across every scale, from the flickering interior of a proton to the invisible bulk of the cosmos. The Higgs is one small, real, hard-won piece of an enormous, unfinished puzzle, and the puzzle has one more twist waiting, the most unsettling of all. Because that quiet self-interaction of the Higgs, the one scientists have barely measured, might mean that the strength of the field, and every mass that depends on it, is not permanent. The stable universe you live in might be balanced on the edge of a change that could erase it. Come back to the valley from before. The Higgs field is like a ball resting at the bottom of a valley, sitting at a comfortable strength, handing out the masses that let atoms and stars and you exist. Everything depends on that ball staying put. Now here is the question that turns cold. Is the ball resting at the lowest point there is? Or is it sitting in a shallow dip with a deeper valley hidden somewhere beyond a hill it cannot see? This is where the Higgs self-interaction, the least measured feature of all, becomes the most important number in the universe. Because the shape of the valley is set by how the Higgs talks to itself. Measure that self-interaction precisely, and you learn whether our valley is the true bottom, safe forever, or a false bottom with a cliff nearby. Scientists have made their best estimates using the masses they have measured, especially the mass of the Higgs boson and the mass of the heaviest quark. And the answer they get is deeply unsettling. It sits right on the knife's edge. The measurements hint that our universe might be in a state physicists call metastable. That means the Higgs field is resting in a valley that is stable enough to last but is not the deepest valley possible. There may be a lower one out there, a state the field would rather be in, separated from us by a hill. For now, the ball sits in our dip, held by the hill in front of it. But it is not at the true bottom, and a metastable state can in principle change. Given enough time or the right violent trigger, the Higgs field could slip over the hill and roll down into the deeper valley. If it did, it would settle into a new strength, a completely different value, and every mass in the universe, every particle's weight, is set by that strength. Think of a snowbank clinging to a steep mountainside. It looks perfectly still. It might sit there for 1,000 years. But it is not at rest at the bottom of the mountain. It is held in place by a delicate balance, and a strong enough disturbance could send the whole thing sliding. Our universe, the measurements whisper, might be that snowbank. Now, before this becomes pure nightmare, hold on to the timescales. Even if the universe is metastable, the calculations suggest it is extraordinarily stable in practice. The hill holding our field in place is so tall that the field would likely sit safely for a span of time vastly longer than the current age of the universe, longer than almost any number worth naming. So this is not a danger for you or your descendants or the stars for an immense stretch of time ahead. But as a matter of principle, it is staggering. The stability of physical reality itself, the permanence of every mass and every law, may not be guaranteed. It may depend on the precise shape of a valley we have only begun to measure, and that raises the darkest version of the question. What would actually happen if the Higgs field did slip? If the ball rolled over the hill and found the deeper valley? The answer is a scenario so extreme that physicists gave it a name that sounds like the end of a horror film. Let us follow the nightmare to its end, carefully, because it is one of the strangest ideas in all of physics. Suppose the Higgs field really is sitting in a false valley, and suppose that somewhere, somehow, a tiny patch of it slips over the hill and rolls down into the deeper valley. What happens then? Scientists call it vacuum decay, and the picture is chilling. At the spot where the field slips, a tiny bubble forms. Inside that bubble, the Higgs field has settled into its new, deeper strength. And inside that bubble, the laws of physics are different. The masses of particles are different. The rules that let atoms hold together may not work at all. It becomes a pocket of space where reality follows a new set of instructions. Now, the terrifying part. That bubble does not stay small. Once it forms, it is more stable than the universe around it, so it grows. Its wall races outward in every direction, expanding at very close to the speed of light, and as the wall sweeps across space, it converts everything it touches into the new reality inside. Stars, planets, atoms, all of it swallowed and rewritten as the bubble expands. Because the wall moves at nearly light speed, you would never see it coming. No warning, no shadow on the horizon. The bubble would reach you at almost the same instant as any light that could have announced it. One moment, the universe as you know it. The next, the bubble arrives, and everything you are made of is converted into something governed by laws that may not allow you, or atoms, or anything familiar to exist. It sounds like the wildest science fiction, but it falls straight out of the equations of the Higgs field. If our universe truly is metastable, it is a real possibility that serious physicists study with serious math. Picture a still pond frozen over on a cold night, the ice looking solid and permanent. Then imagine one tiny crack forming at a single point, and that crack racing across the entire pond in a heartbeat, shattering the whole frozen surface faster than your eye can follow. Vacuum decay is that crack, spreading not across a pond but across the universe, and it does not shatter the ice. It rewrites what ice is. Now, breathe. The same calculations that raise this possibility also say it is extraordinarily unlikely to happen for an immense stretch of time, far longer than the age of the cosmos so far. The hill holding our field in place is, by all estimates, enormously tall. This is a curiosity about the deep future and the deep nature of reality, not a threat looming over anyone alive. But as a window into how much the mass problem still hides from us, it is unmatched. The particle the world crowned as the source of mass may be resting in a state that is only temporarily safe. The strength it's settled into, the strength that gives you your weight, might not be the final word. The universe might be balanced above a change it cannot see. That is how far the mystery of mass reaches. And it means the search is far from over. Scientists are already building toward the next great push, hunting for the answers the Higgs left behind, with plans for machines that dwarf anything we have built before. So where does the search go from here? The Higgs was found, the field was confirmed, and yet, as we have seen, the deepest questions about mass remain wide open. Physicists know this better than anyone, and they are not standing still. They are dreaming up the tools to chase the answers. The single most wanted measurement is the one we keep circling back to. The Higgs talking to itself. That self-interaction, the feature that sets the shape of the valley and decides whether our universe is truly stable, has barely been glimpsed. Pinning it down precisely is the great prize of the next generation of physics. Measure it, and we learn the true shape of the field that gives everything mass, and whether the ground beneath reality is solid or a false floor. But measuring it is brutally hard. It requires slamming particles together to make two Higgs bosons at once, so scientists can watch them interact, and that kind of collision is fantastically rare. The machine near Geneva can barely produce enough of them. To truly nail the measurement, physicists need something bigger. Much bigger. So they are designing new machines that stagger the imagination. One leading proposal is a collider so large it would circle underground in a ring roughly 60 miles around, more than 3 times the size of the current giant. Picture a tunnel long enough to loop around a major city and its whole suburban sprawl, buried deep beneath fields and towns, built to smash particles at energies we have never reached. Another bold idea is a machine that collides a strange, heavy cousin of the electron. Particles so unstable they must be used within a flash of being created. Building it would mean solving engineering problems no one has cracked yet, racing to collide particles before they fall apart. It sounds nearly impossible. Physicists are working on it anyway. Why go to such lengths? Because the answers to the biggest questions, where mass truly comes from, why the Higgs is so gentle, whether hidden partner particles exist, what dark matter is made of, all live at energies just out of our current reach. Push a little higher, look a little closer, and the door to the next layer of reality might swing open. The history of physics is a history of building a bigger machine and finding a whole new world inside. Think of it like the great voyages of exploration. For centuries, ships could only travel so far before turning back, and vast regions of the world stayed blank on the map. Then someone built a better ship, one that could sail farther and survive rougher seas, and entire continents came into view. The new colliders are those better ships, built to sail into a region of reality no experiment has ever reached, where the real origin of mass may finally be waiting. There are no guarantees. The new machines might confirm everything we expect, or they might shatter our theories and force a total rewrite. Either way, physicists win, because a surprise is often more valuable than a confirmation. A surprise means there is something new to learn. So the story of mass is not a finished book. It is an open frontier, with the next chapters waiting to be written by machines not yet built. And when we step back and take in the whole picture, the honest scorecard of what the Higgs did and did not solve, the scale of what remains is breathtaking. Let us lay out the honest scorecard. After everything, what did the Higgs boson actually solve, and what did it leave untouched? Line it all up, and the picture becomes clear and humbling. Start with the win, because it is real. The Higgs field explains why fundamental particles have any mass at all. Without it, electrons and quarks would be massless, racing at light speed, unable to form atoms. The Higgs makes atoms possible. It was one of the greatest confirmations in the history of science, an idea from a walk in the Scottish hills proven true by the largest machine ever built. That achievement stands, and it always will. Now the ledger of what it did not solve. Take a breath, because the list is long. The Higgs gives you only about 1% of your body's weight. The other 99% comes from the storm of the strong force inside your protons, energy frozen into mass by Einstein's equation, so complex that supercomputers strain to calculate it. The Higgs never explained that part at all. The Higgs cannot explain its own strength. The math says it should be crushingly heavy, yet it comes out feather-light, balanced on a knife edge for reasons no one can find. The elegant fix, supersymmetry, was hunted for years and never appeared. The Higgs struggles to explain the mass of the ghostly neutrinos, which were supposed to weigh nothing, and turned out to carry a whisper of weight through some door the plain theory never had. The Higgs says nothing about dark matter, the invisible stuff that outweighs all ordinary matter 5 to 1. It says nothing about dark energy, which outweighs everything else and pushes the whole universe apart. Together, those two make up the overwhelming majority of the cosmos, and the Higgs governs none of it. The Higgs does not explain the bizarre pattern of particle masses, why they come in 3 families climbing steeply in weight. It does not explain why matter beat antimatter and let anything exist. And it says nothing about gravity, the pull that shapes galaxies, which is the other half of what mass even means. On top of all that, the Higgs field may be resting in a false valley, its stability only temporary, the strength it settled into perhaps not permanent at all, so here is the full reckoning. The particle the world crowned the God particle, the one headline said gave everything its mass, explains a thin sliver of ordinary matter, cannot account for its own gentleness, and stays silent on the vast majority of the mass and energy in the universe. Picture a detective closing one small case with great skill, solving exactly who took the missing wallet, while all around the biggest mysteries in the city remain wide open, unsolved, barely investigated. The Higgs cracked the wallet case. The great mysteries still stand. None of this diminishes the discovery, it reframes it. The Higgs was never the end of the story of mass. It was one hard-won clue in a mystery far larger than anyone admitted when the champagne was flowing in the 2012, and the size of what remains is not a defeat. It is an invitation. Because a question this deep, this wide, this unfinished, is exactly what pulls the next generation of minds toward the frontier. So where does all of this leave us? Standing at the edge of the deepest question a person can ask about their own body. Why do I have weight? Why does anything? Trace it back through everything we have seen. Your weight is not one simple thing with one simple cause. It is a layered mystery, built from at least 2 completely different sources that barely speak to each other, wrapped inside a cosmos where most of the mass and energy remains totally unknown. A sliver of you, about 1%, comes from the Higgs field, that invisible ocean filling all of space, gripping the fundamental particles as they swim through it. The rest of you, the crushing majority, comes from the storm of the strong force inside your protons, pure energy locked into weight by the most famous equation ever written. Two sources, one quiet field, one raging storm. And even together, they only account for the ordinary matter that makes up a few percent of the universe. Look outward, and the mystery only deepens. Invisible dark matter, 5 times heavier than everything you can see, made of who knows what. Dark energy, heavier still, pushing the cosmos apart for reasons that produce the worst prediction in the history of science. A vacuum that fizzes with energy, particles flickering in and out of the void, empty space that is anything but empty. And threaded through all of it, questions with no answers. Why is the Higgs field so gentle when it should be monstrous? Why do particle masses follow such a strange steep pattern? Why did matter survive its ancient war with antimatter? Why does mass create gravity, the one thing the Higgs cannot touch? Whether the ground of reality itself is truly stable, or only resting in a valley it might one day leave. Here is the thing to carry with you. The universe let you believe for a while that mass was solved. A single particle was found, a nickname was coined, and the case seemed closed. But the deeper anyone looks, the more the simple story dissolves into something vaster and stranger and far more alive with mystery. That should not feel like a letdown. It should feel like standing at the shore of an ocean everyone thought was a puddle. The Higgs was a real and beautiful discovery, and it opened a door. Behind that door was not an answer, but a hall of even bigger questions, stretching further than anyone expected. You're made of storms and frozen energy, and a whisper of an invisible field. You're built from leftover matter that barely escaped annihilation at the dawn of time. Most of the universe around you is a substance no one has ever identified, pushed apart by a force no one can explain, and the very weight of your body connects through a chain of physics to some of the deepest unsolved puzzles in all of science. The mystery of mass is not behind us, it is spread out ahead of us, enormous and waiting, from the churning heart of a single proton to the invisible bulk of the entire cosmos. One particle did not close the book, it only turned the first page, and the people who will write the next pages are already picking up their pens, aiming their machines at the dark, chasing the real origin of the weight of everything. So we end where the real work begins, at the frontier, at the blank edge of the map, where the biggest questions about mass are still waiting for someone to answer them. Everything we have traced points to one honest conclusion. The origin of mass is one of the great unfinished projects of human understanding. We have real pieces, the Higgs field, confirmed and beautiful, the strong force and its storms building most of our weight, Einstein's equation, turning energy into matter in every atom you own. These are genuine, hard-won truths, and they are astonishing. But the pieces do not yet make a whole. The gaps between them are enormous, and inside those gaps sit the deepest mysteries in physics. Where does the Higgs field's gentle strength come from? What is dark matter made of? Why does the vacuum carry so little energy when it should carry so much? Why does mass pull as well as resist? And beneath it all, the dream physicists have chased for a century, a single theory that ties every force and every particle and every kind of mass into one clean, complete picture. That dream is why they build the machines. Right now, engineers and scientists are drawing up plans for colliders that would circle underground for tens of miles, sail into energies never reached, and hunt for the particles and answers the current machines cannot find. Others are working on wild new designs, on detectors buried deep in the earth waiting for a single flash of dark matter, on telescopes measuring the push of dark energy across billions of miles of space. Each of these is a ship built to sail past the edge of the known map, and history says something waits out there. Every time humans built a better instrument and looked closer at reality, they found a new layer nobody had imagined. Atoms hid inside matter. A storm hid inside the proton. A field hid inside empty space. There is every reason to believe more layers are waiting, and one of them may finally reveal where the weight of everything truly comes from. Here is the part worth holding on to. You're not just a spectator to this, you are the mystery. The question of mass is not some distant abstraction floating in a lab. It is the weight of your own hand, the pull of your own body toward the Earth, the storms raging inside every proton in your bones at this exact moment. When scientists chase the origin of mass, they are chasing an answer to what you are made of and why you weigh anything at all. The Higgs boson was a triumph and a beginning. It taught us that the universe hides its deepest rules in the emptiest places, and that a single quiet field can shape all of reality. But it also taught us humility by solving one small corner of the puzzle and revealing how vast the rest of it truly is. The mystery of mass is still open. It stretches from the heart of a proton to the far edge of the cosmos, and it is waiting for the curious, the stubborn, the ones who refuse to accept a closed case that was never really closed. Maybe one of them is listening right now. The weight of everything is still an unanswered question. The search for its answer has only just begun.